Okay guys, let's take a look at today's lesson. So today we're going to look at combining functions and inverses of functions. So this whole unit is on functions, and so we're just looking at all different kinds of parts of functions. So there's a couple of different ways that we can combine functions. These first four right here, that we could add functions together, subtract them, multiply them, or divide them. Because so those are typical ways we could combine functions. I'm writing both of these notations just so that we're familiar with either one. They both mean the same thing. Sometimes you'll see it written like this, sometimes you'll see it written like that. Just want you to feel comfortable with either notation. So these are all the different, add, subtract, multiply, divide type of combinations. So our domain is typically, I guess, students don't typically have a problem adding, subtracting, multiplying, dividing functions. It's where the domains come in that there's a little bit tricky. We need to understand that the domain of the combined function is the intersection, this symbol means intersection, is the intersection of the domains of the two original functions. So that's something that we'll be practicing on the next slide, but that's how we would find the domain. Is we would find the domain of f, we would find the domain of g, and then we would intersect those. Well, what does intersect mean? Intersect means that we would use only the common numbers in both domains. Okay, so if there's a number that occurs in one domain and not the other, we would leave that out. We would not include that. An extra issue we need to be aware of is if we are dividing functions, there may be an additional restriction for us. If g being the denominator, if there's some number that causes that to be 0, that would be an additional restriction for us in addition to just taking the intersection. Okay, so we'll look at an example like that on the next slide. So this is a way to algebraically combine functions, taking their equations and adding them together and such. There's also a way to graphically add functions. That's what this is talking about. You can actually add them by graphical addition. What does that mean? You would basically, so if we had two functions that we were adding together, let's say, just for fun, let's say a line and a parabola. How would we add them graphically? What would we do? Well, what we would do is we would go to, say, an x of 1, and we would look to see what the y value of this function is and the y value of that function, and we would add them together. So our new point for our where we're adding them together would be 1 comma whatever the sum of those two was. And you would need to, if you're adding them graphically, you would need several points. I would just do integer points. That would probably be sufficient. Several integer points to kind of see what the shape of the new added graph would look like. Okay, so that's how you would do graphical addition. I don't have an example of that on the notes, but there are some problems like that on the daily work. Again, just like I was explaining before, I can't show one of everything, or I would be up here talking the whole time, which I would really not like. So you guys need, hands-on work. Okay, so that's what you would be doing if you were adding them graphically. There's another way to combine functions, and that is use a composite function. You probably remember that from last year. There are two different notations that go with composite functions. These mean the same thing. That f of g thing of x is the same thing as f of g of x. It means the same thing. And that's where we would insert one function inside of another and simplify. That's what a composite function would be. Another topic that you may or may not have talked about last year is one-to-one, a function being one-to-one. I'm sure we are all familiar with the vertical line test, right? The vertical line test helps us determine whether something is a function or not. Right? Remember the vertical line test? Well, there's also a horizontal line test for one-to-one functions. Because one-to-one, maybe we're not really sure what that means, but let's look at the test. So if let's kind of get rid of this right here. Let's just use, for example, the parent parabola, y equals x squared. Let's use that as an example. If I were to do the horizontal line test, it touches the function more than once. That means it is not one-to-one. The parent parabola, y equals x squared, is not a one-to-one function. What about y equals x cubed? Yeah, that is a one-to-one function. It doesn't matter where I do my horizontal line, it's still going to go only through once. So that's a different kind of test for you, the horizontal line test. That will help us determine if it's one-to-one. Why is that a big deal? Well, a function, in order to find its inverse, it has to be one-to-one. One-to-one functions have inverses. Okay, so let's look at the inverse. That kind of leads us to our next topic, is inverses. So if f is one-to-one and it has a domain of A and a range of B, then the inverse, f negative 1, we looked at that with trig. We talked about that, right? It's not 1 over f. That is just a special notation that means inverse. So the inverse of f would have the domain and range switched, right? Its domain would be B and its range would be A. And when we're finding inverses, to find them algebraically, we would simply switch the x and the y and solve for y. So here's the original function, x and y. We would flip them, and so the inverse would have, the y in the place of the x and the x in the place of the y. And if we were doing that algebraically, we would then solve for y if possible. All right, so algebraically, there's a test. We have a test. Let's say we're given two functions and we're asked if they're inverses of each other. This is the algebraic test that will determine whether that's true or not. What would we do? Well, we would do a composite. We would do the inverse of the regular function. Then if I get an x, yes, they're inverses of each other. I would do the function, the inverse inside of the function of the inverse also, and I should get x as well, if they're inverses of each other. They're both of those computations, once they're simplified, we should get x. So that's the algebraic way to determine if functions are inverses of each other. There is also a graphical way to determine that. It's a good technique for graphing. It's maybe a little bit more difficult or not as precise, I would say, as the algebraic one. What we would do is we would graph both of the functions, and to determine whether they're inverses of each other, they would have to be symmetrical over the line y equals x. That would be the graphical way to determine if functions are inverses of each other. We would look at their graphs, we would graph them, and determine whether they are, reflected, if that one function is reflected over the y equals x line to create the other function. So that's a couple of ways to determine whether they're inverses or not. This is the algebraic technique, this is the graphing technique. Okay, so a lot of that is probably review, maybe not everything. Is there questions about the concepts before we start some problems? We okay so far? Okay, let's go to the next slide. All right, so our first example, we have 1 over x minus 2 is f of x, and g of x is root x. We're asked to add those functions and divide them, and we're also asked for their domains. So we're combining them with, operations, addition, subtraction, that kind of thing. So what I would like to do, what I would suggest that you do, is find the domain of each one individually, and then do the intersection of the domain to see what the domain is going to be of actually all of them, except maybe perhaps the division one may be extra restricted. But all of them are going to have at least this domain. So let's do that. So the domain of f, and when we find domains, really we're looking for things that don't work, not for things that do work, which seems a little bit weird. We're looking for things that don't work. What x value could I come up with that would not work in that f of x, which is 1 over x minus 2? I mean, 2, right? 2 is not going to work, and we have to think, would there be any other x value that would not work? And what I mean by not working is it would make the equation undefined. It'd make the function undefined. And really all the other x values, anything you can think of, would work in there. So our domain for this one, and I'm going to do both interval notation and set notation throughout the lesson, just so you have a feel for both types of notation. Unless the directions specify, you can do whichever one you want, whichever one is easier, makes more sense to you. So we're going to do interval notation first. So this will be going from, this is our domain for f. We would go from negative infinity to 2. We wouldn't include 2, and then 2 to infinity. That would be our domain for f. Now let's look at the next function, g. So with radicals, we know that there are problems when the value under the radical is negative. That's a problem. So what we do is we take whatever's under the radical and force it to be greater than or equal to 0. Right? That's how we algebraically determine what the domain is. This is just x, right? X has got to be greater than or equal to 0. So in interval notation, I would include 0 and go to infinity. That would be my domain of g in interval notation. Okay, so let's just find the intersection of those, because this domain is going to apply to everything except perhaps the division one. So let's find the intersection. So the intersection is what numbers occur in both domains. Those are the numbers that we're going to use in our combined domain. I think we can see this one, the g's domain is greatly restricted. There are no negative numbers in here. So that means I would have to take all of those negative numbers out. Okay, so we would start at 0. So our domain would start at 0. And let's see how far we would get. It looks like we would get until 2, because we can't include 2, right? So it goes 0 to 2. We can't include 2. And then we would go from 2 to infinity. That's our combined domain. And that will apply to all of the addition, subtraction, multiplication ones. We may have to, with f over g, may have to do an additional restriction. We'll wait till we get there. Okay? So let's do the addition of these. So 1 over x minus 2 plus root x. Now that's the sum of those. Let's talk about whether we, go through the process of finding common denominators and add them together, or whether we don't. If I have a mixture like that, like a rational and a radical, you really don't need to add those together. Physically, find a common denominator and add them together. Okay? If that's a mix like that. Or let's say I'm adding a trig function and a rational. You really don't need to add those together. But if I'm adding two rationals together, I should really add them together. Add them together, find a common denominator, and that kind of thing. So just keep in mind what our simplified version would look like. And if you're unsure, you can just add everything together if you want. If you're not sure if it should be added or not, I certainly could add this together. It wouldn't be that hard, right? It would be 1 plus square root of x times x minus 2 over, x minus 2. It wouldn't be that hard. It just would be more complex than what I have, so let's not do that. So this domain applies to f plus g. We're good there. Now let's do f divided by g. So that would be 1 over x minus 2 over root x. And I'm going to put that over 1. It's kind of squished in there. Because it's a complex fraction. Now that we know we cannot leave a complex fraction. That's like no way. So let's fix the complex fraction. We would flip that up. We get 1 over x minus 2 times the square root of x. Okay, so that would be my f over g. So what we're going to be required to do if it's a division one is we need to see if some of these numbers that we included in the original intersection of the domains we have to leave out. It's possible that we may have to leave something else out. If we look at this domain, 2 is already out. But 0 now has to be out, doesn't it? For this particular one, 0 would cause the denominator to be 0. So I can't use this domain for the division one. Okay, I can use it for the other three, addition, subtraction, multiplication, but I can't use it for the division one. I need to do a separate domain for the division one. So let's do the separate domain. I'm going to have to leave the 0 out, and the rest of it is fine. Okay, so our answers, what do our answers look like? So here's our f plus g answer, and the domain for all, f plus g, f minus g, f times g. This would be our f divided by g answer and its little domain. He gets its own special domain. He's pretty excited about that too, I'll say. Okay, we okay with the addition and subtraction, those combinations? All good with that? All right, let's look at the composite functions where we insert one function inside of another. So let's do g of f of x. So g of f of x. So I'm going to insert the function f inside of g, and that gives me 2 minus root x. Now, unfortunately, there's nothing we can do to simplify that. That's just as simple as it's going to get. All right, so let's work on its domain. We have a lot going on there. 2 different radicals. So let's investigate what happens. When I'm investigating the domain of a radical, what I do is I take the quantity underneath the radical, so the 2 minus root x, and I force it to be greater than or equal to 0. We know that that has to be true, right? Because if it's less than 0, then it's imaginary. And our domain just includes real numbers. It doesn't include imaginary numbers. So this is the domain of the real domain. So what I would do, I would move the root x over. I would square both sides. And I know that x needs to be smaller than or equal to 4. Now that kind of makes sense. Consider what would happen if x were 9. That would be a problem, wouldn't it? And it's not, 9's not included in here. So that domain makes sense. We know x needs to be smaller than or equal to 4. So we've taken care of one radical. Let's take care of the other one. We have another radical that we need to consider, and that's this one. Now luckily it's just x. X, must be greater than or equal to 0. So these are the 2 domains, the domain of each of those 2 radicals that we need to intersect. What numbers do they have in common? Because we can't use any number outside of those intervals, because that, right, it wouldn't work. So let's see, x needs to be smaller than or equal to 4, and x needs to be larger than or equal to 0. That's a very small area, isn't it? So if we're doing, I'll stick with interval notation for just another round. So if we're doing interval notation, our domain would start at 0 and include 0, and it would go to 4 and include 4 and stop. So here's our composite function, and here is our domain. Okay, we okay with that? Okay, the last composite, we're going to do f of x. So f of x. So we're going to insert f of x into f of x, which I know is always just weird, but that's just what we're going to do. So that's what we just did. We inserted f into f of x. Now we can simplify that. That looks a bit of a mess. So what I would like to do is write that as an exponential function, so I can get a better feel for what's going on, and then I'll change it back to a radical. Because we're given a radical, we really need to give them back a radical, but this kind of is confusing. So I'm going to rewrite it as exponential. That would be x to the 1/2 to the 1/2. Right? That's what that would be written as if I were writing it in exponential notation. Exponents are not going away. Those rules, we need to have those really firm in our brains. Right, so this is power to power. What do we do with exponents that we do power to power with? We multiply them, right? So this would end up being, when I simplify that, this would be x to the 1/4. In exponential notation, that's what it would be. Now we need to move it back into a radical because they gave us a radical, so we've got to honor the form that they used. So this would be a 4th root of x. This would be my f of x is the 4th root of x. Okay? So domain. That's a pretty straightforward domain, right? It's an even root. All even roots can't be negative, right? You can't have anything under there that's negative. So this domain would go from 0 to infinity. Okay, and those are the combinations of functions. How are we with that? Okay? All right, now let's look at finding inverses. That's our second topic for the day, is finding inverses. So algebraically, when we find an inverse, we switch the x's and the y's. Wherever there's a y, I put an x. Wherever there's an x, I put a y. So that's what we're going to do first. Let's switch them. So we know this f of x means y. So that's going to be x equals y minus 1 over y plus 2. Okay? Alright, so what I would do is I would cross multiply. I would cross multiply first. That would be my first step. So that would be x times y plus 2 equals y minus 1. Okay, we all okay with that? Then what I would do is I would distribute. I want to lift the parentheses. This is a fairly complex one. Okay, we need to, hopefully we're fine and following along. This is a complex one. So I need to lift the parentheses, so I'm going to distribute the x. So I have xy plus 2x equals y minus 1. And you may be thinking, oh my gosh, there's so many y's. I'm supposed to solve for y. What am I going to do? Okay, what would I do? Well, I would need to isolate the terms with a y in it. I'm going to move the terms with a y in it all to one side and everything else to the other side. That's what I'm going to do. And so let's see, let's move the y terms to the right and everything else to the left. So I have 2x plus 1 equals y minus xy. Okay, so I do at least have the y's isolated on one side. Now I need to think of a way to just come up with one y. And that would be factoring. What if we factored a y out? Can't we do that? Right? We factor a y out. So we have y times 1 minus x equals 2x plus 1. Whew, okay, great. We're making progress. We just have one y, and now we can just solve for the y. Let's divide both sides by 1 minus x. So we have y equals 2x plus 1 over 1 minus x. And now they like, it is the inverse, and the original one was called f of x, so I'm going to use their notation. I'm just going to call this would be f negative 1 is 2x plus 1 over 1 minus x. Now the other task that we're going to be challenged with is to find the domain. Okay, what I would suggest is to take the original function and find its domain and range, and then for the inverse we'll just flip them. Okay, so let's do that. Let's take the original, let's work on this original function right here, and we're going to find its domain and range. So the domain, pretty straightforward. I think we'll be fine with that. You know, we can't have a negative 2, right? So we would go negative infinity to negative 2, union negative 2 to infinity. That's my domain. The range is a little bit more challenging. What possible y values could we have? Well, one way to battle that would be to graph it. And that's what I'm going to do. I'm going to graph it, or in your head. If you could think about the graph in your head, you don't necessarily have to write it down, but we need to know what y values are involved. Right? So we just got finished graphing rationals. We just got finished with a unit graphing rationals. We know how to do that. So let's do that. So looking at this, we know that there's a vertical asymptote at negative 2. And we also know that there's a horizontal asymptote at 1. The zeros of this, remember we set the numerator equal to 0. That's how we get the zeros. That would be at 1. So when x is 1, y is 0. Is it possible to break through the horizontal asymptote? With the inverses, it should not be possible, because on the inverse, that's going to be the vertical asymptote. So we shouldn't have any breakthroughs here. That wouldn't be a one-to-one. That would be a problem. We shouldn't have breakthroughs. And we'll, as we go on, we'll investigate that further. I see negative 3. I would try a point at negative 3, and that turns out to be 4. So that's up here. So my range goes from negative infinity to, let's see, we go up and we can't have 1. And then from 1 to infinity. Now the inverse is going to have those flipped, right? The domain and range are going to be flipped. So let's do that. So this inverse, the range of the original would be the domain of the inverse. And the domain of the original would be the range of the inverse. Now let's look at our domain and range and see if it makes sense with the problem, our actual inverse equation. All right, so let's look at our inverse equation. Does it make sense that the domain doesn't include 1? That makes sense, doesn't it? Yeah. What would be our horizontal asymptote of this inverse? Can we tell what that would be? -2. It would be -2, right? Here, -1, 2. And so that makes sense that that would not be part of our range. So this makes sense. Okay, so this would be the domain and range of the inverse. Okay, we okay with that? All right, last problem. So we want to find the inverse of this. So we're going to do the same thing. We're going to switch the x and the y. So x equals square root of y minus 4. We want to isolate the y, so we're going to square both sides. So y equals x squared plus 4. So f -1 equals x squared plus 4. Now I hope we recognize there's probably some significant problems with that. We're going from a radical to a whole parabola. That's an issue. So let's work on domain and range. So let's work on the domain and range of the original. So the domain, and this time let's do set notation. Let's do, well, not the full formal set notation, but let's do inequalities. So to find this, I would need to say x minus 4 has to be greater than or equal to 0. Right, that's what we do with radicals. We force the inside part to be greater than or equal to 0. So I solve for x, and I get that x is greater than or equal to 4. So my domain would be x being greater than or equal to 4. Now let's look at the range. The very smallest number, what happens when I put a 4 in here? My y value is 0. And as I put larger numbers in here, 4, 5, 6, 7, 8, what happens to my y value? Gets larger, right? So my range is y is greater than or equal to 0. Okay, we okay with that? So now let's reverse that for the inverse. So the original's range is going to be the inverse's domain. So x in the inverse needs to be greater than or equal to 0. And the range will be the original one's domain. So y is greater than or equal to 4. So let's see if that makes sense. What happens when x is greater than or equal to 0 with my parabola? Do I get to have the whole parabola? No, I only get half of it, right? I get half of it. I get the part from 0 to infinity. So we know how to graph this parabola, right? That parabola would look something like that, right? The full parabola. But the inverse of this won't include this part, so we wouldn't have that part there. So let's erase that part. This side right here would not be there. So let's see if the domain and range makes sense. So it does make sense that x has to be bigger than 0. Does it make sense that y has to be bigger than 4 or equal to 4? Right, that works, right? Are we okay with that? Okay, great.